Meta operates large-scale data warehouse. In the era of agents, how does its data access evolve? My name is Cam, software engineer at Meta. Today, with my colleague Uday, we'll talk about how Meta built a Agentic solution to its data warehouse access and how this approach helped us scale out and streamline the process. Meta's offline data system spans across data warehousing, stream data processing, monitoring, and observability. It supports a wide range of use cases across data analytics, monitoring, and service operation. It also supports AI, machine learning, including generative AI. We see the agents bring the potential for us to streamline access and minimize risk. Security remains paramount in everything we do.
That is an excellent point, Cam. After all, Meta has billions of users, and some of this data is user data. Some of it might even be sensitive. And at Meta's scale, hundreds of teams manage access to this data, and tens of thousands of engineers are working on tools and pipelines that process this data to deliver the products that Meta's users enjoy. In such a dynamic environment, keeping this data secure is, while it is challenging, it is also important that we get it right. So in the rest of this talk, we are going to focus on how we are rising up to this challenge using agentic solutions.
So in the past, we scale out the warehouse access management by organizing it into a hierarchical structure. It starts from the need. So we have the tables containing data and the data pipelines producing them and the dashboards consuming them. And those data are organized into projects that are organized, managed by uncles. And they are further rolled up into teams and organizational hierarchy. We further model business needs as roles using role-based access control, which align with this hierarchy and other dimensions such as data semantics. And with AI, efficient data access becomes even more important. And the scale continues to grow and the access pattern becomes more complex.
To understand the complexity that Cam is talking about, it helps to visualize our data warehouse as a graph. In this graph, each node represents some asset like a table, a column, a dashboard, and things like that. While each edge in this graph is representing a data processing activity, a pipeline, or use of an interactive tool to understand the particular data. In old days, when most of data analytics was rules-driven, the access of this warehouse was very partitioned and accesses were very local. If you want to know where is the data that you need to use, go and ask your colleagues on your team or go look at the diffs that they have written. At the same time, if an data access request comes in and you want to figure out whether to approve the request or not, just look up the person in the org hierarchy. Are they working on a team that is related to you? If they are, approve it. Otherwise, escalate. However, over the last several years, AI is making the access patterns more and more complex. Remember, AI can ingest data from valid, seemingly unrelated sources and can provide unparalleled insights into that data. However, because of that, our users or our engineers don't always know where the data they want exists. And also the approvers don't know whether this person who's accessing the data actually needs access to that data. In this kind of complex environment, it is really difficult to manage warehouse access using human input. And this is why we are looking at AI to help us.
Continue from what Uday just shared, right? The system is becoming more complex, both in size and access patterns. And human and agents are working more cross domains and with AI as a key driver. So they pose unique challenges. But in the meantime, and we also see AI and agents offer solutions to this problem. So here we are talking about how we are going to build agentic solution and use human-agent collaboration to solve this problem. We are taking a product-oriented approach and making sure that everything we build natively integrate into data tools and people's workflows.
Before we jump into the solution space, let us understand a few key terminologies. First of all, in our access request and access approval problem, there are two key personas. On the left-hand side, we have the data user who needs access to the data and who processes the data to deliver the products. Whereas on the right-hand side, we have data owner who is responsible for safeguarding the data and managing access to that particular data. To model this interaction correctly, we also define two agents. On the left-hand side, we have data user agent, which acts as a negotiator for the data user. And on the right-hand side, we have the data owner agent, which acts as negotiator for the data owner. These two agents negotiate with each other to make sure that the necessary data is discovered, accesses are requested, and accesses are granted safely, securely, but in an end-to-end and seamless fashion.
So in today's talk, we'll share how we model warehouse data access as a multi-agent problem and evolve data warehouse infrastructure to support those agents. And then we'll do a deep dive of an end-to-end use case and conclude the talk with recap and sharing of our future work. So first, we'll dive into the user and owner agents, as Uday just shared. In this multi-agent system, data user agents assist data users to suggest alternatives or request access. Data owner agents help operate and manage access. Those two agents collaborate to streamline the process when needed. We separate them out to decompose the problem and give each of them its own focus. Let's take a closer look at the data user agent. It's not a single monolithic agent, but consists of three specialized sub-agents, triaged by a triage agent. The first sub-agent focuses on suggesting alternatives. When users encounter data access restrictions, there are usually alternatives available, either less restricted or unrestricted tables. They can also rewrite queries to access unrestricted columns or use curated analysis instead of writing queries by themselves. In the past, those informations are usually tribal knowledge or spread across a large volume of documents. But with large language model and agents, we are able to synthesize the information and use agents to communicate that with data user and guide them through the process. The second agent enables low-risk data exploration. Warehouse tables usually have a large volume of data, but users usually only need to access a tiny fraction of that. But how do we enable such low-risk and task-specific data exploration? And Uday will dive deeper and in a later slide. The third sub-agent works as a helper, helps the data users to draft permission requests, negotiate with data owners, agent to obtain access. Throughout the process, we remain strong human oversight. But we believe with time, more and more of them will operate more autonomously. Let's take a look at the data owner agent side. It consists two sub-agents, security operation and access management. The security operation agent operates like a junior engineer. And when they join a team, they follow the SOP, standard operating procedure, which documents how the access should be managed and help the team operating the incoming permission requests. The second sub-agent, an access management agent, proactively optimize access rules. So this is an extension to our rule mapping process, but allow much deeper analysis of the semantics, content, and past interactions. So how do we evolve our data warehouse to support those two agents? As we mentioned earlier, we organize data warehouse in a hierarchical structure to scale out access management. How do we evolve it? Large language model and agents speak in text. So the hierarchical structure of data warehouse nicely mapped to a folder structure. Assets are resources, and the hierarchical structure becomes folders. And this becomes a nice read-only summarized view of the data warehouse. And this structure is not only for data resources. And the SOP document we talked earlier, which is basically document about data practice derived from rules, wikis, and past interactions. So they are synthesized and represented as text and in the structure. So, and use them to guide both data users and data owners. In addition of organizing resources and the SOP and policies into a hierarchical structure, context management is very important. Basically, we need to decide what information is relevant to agent so they can load it into the context. We are considering 3 scenarios. We call the first scenario automatic context. When a user discovers data and access it and being blocked, we know exactly what is being accessed and who is accessing. So the exact context can be loaded and into the agent. The second we call static context. So the data users can explicitly choose what to focus on, such as a project, or it can be expanded from the automatic context. So for example, when a user is blocked, we can extend to alternatives in the same project. The third one is called dynamic context. It allows the agent to filter resources by dynamic criteria, such as data semantics and similarity search. Besides context management, another important aspect is intention management. So in warehouse data access, we call intention management business needs. It's basically the why of the data access. We model intentions in 2 ways, explicit and implicit. In explicit intention management, data users basically tell the system what they are working on by assuming a role. So this allows us to model standardized intentions. And once a role is assumed, the agents can pull in relevant role information. However, not every intention can be standardized. This is where implicit intention comes in. Imagine a data user was woken up during midnight because of the pipeline failure. And such events and related activities can be used to derive the intention. And subsequent actions from the same user is likely related to that intention. So then I'll hand over to Uday to do a deep dive of an end-to-end use case.
Now let's look at how all of these components come together to solve an end-to-end problem. Just to recap, we have data user agent and data owner agent, where user agent acts as negotiator for the data user and owner agent acts as negotiator for the data owner. But how does this apply to a real life scenario? In real life, a data access workflow begins with data discovery, followed by exploration, where the data user quickly looks at the data to decide whether the data is useful or not, and then finally moving to data use. Data exploration is where we see a lot of friction happening because users have to apply for access for data that they may not even use, and owners have to field requests for data that users may not need. And with our agentic solution, we are looking to seamlessly solve this particular problem. To solve this problem end to end, we rely on 4 key capabilities. First and foremost, our system is completely context driven. The context comprises both user context, like user's job role, what user is trying to do, and owner context, such as what are the standard operating procedures on the data, what is the shape of the query, and such thing. However, to make context-aware decisions, the decisions need to be fine-grained enough. Because remember, query forms a big part of the context. And because of that, to enable these capabilities, we have implemented a fine-grained query-level permission system. The third key capability is data access budget. Remember, we are working on data exploration phase, where user does not need access to tons of data, but only a quick preview of the data. To enable this, we allow users to have a small amount of data access budget, which gets renewed on a daily basis, but it protects the data from overexposure in case the AI system made a wrong decision. But finally, no AI system is perfect. And because of that, to safeguard our data from mistakes of AI agents, we also implement rule-based safeguarding engine. With that context, let's take a deeper look into what our system looks like. On the left-hand side, we have the data user agent. The data user agent taps into the user activities tool to capture information such as what the user is working on, what diffs they are creating, what tasks they are working on, any design documents that they might have written. It also supplements this information with user's profile, their job role, position, organizational hierarchy, and things like that. It builds this context and presents it to the data owner agent. The data owner agent supplements the user agent provided context with its own context, such as shape of the query, if the query is doing any anonymization, the sensitivity of the data the query is accessing, standard operating procedures on that data. And it takes all of this context into account to issue a decision recommendation. This decision recommendation gets fed into our rule-based safeguarding system, and the safeguarding system is the one that issues the final decision. Note that none of the capabilities we are talking about here are that new. For example, user activities tools have existed forever. Org hierarchies have existed forever. Query analyzers have existed forever. What is new here is we are taking all of this unstructured information and distilling key insights from this information using a large language model and then making a decision based on those insights. Okay, that makes sense. But is it any good? Does it actually work? That's the key question. To answer this question, we built a data set based on our historical logs. So this data set comprised the various access requests the users have made, the justification they provided as part of those access requests, the decisions that were made by humans on those access requests, and the queries the users ran subsequent to the grant of access. We took this data set and simulated the partial data preview system, and we calculated acceptance recall rate and rejection recall rate. Acceptance recall rate measures what fraction of requests that were approved by humans were also approved by our system. And rejection recall rate measures what fraction of requests that were rejected by humans were also rejected by our system. It turns out our overall recall rate is 90%, with acceptance recall rate of 73% and rejection recall rate of 100%. What that means is our system is conservative and tuned towards safety. The acceptance recall rate of 73% means 27% of the users had to apply for access. But that is okay. At least 73% users were unblocked immediately. And from data owner standpoint, their workload went down by 73%. And that is a huge win. But no AI system is complete without a feedback loop and continuous evolution. To enable this, every query and every request that is subject to PDP gets logged in a secure system. The justification context and acceptance or denial context, everything gets logged. And we audit this and we monitor the quality of the sales system on an ongoing basis and detect any divergence or deviation from what is expected. We are also looking to take this data set, annotate it, and feed that back into our training systems so that our models could be fine-tuned and over time could become better.
So just to recap, and in this talk, we covered three key areas. So first, we covered how we model warehouse data access as a multi-agent problem, and how we build user and owner agents and to solve this problem. We also covered how we evolve the data warehouse infrastructure to supporting building such agents, and including organizing resources and the SOPs and policies, and modeling the context and the intention. We then dive deep into how we do partial data preview to enable a end-to-end use case. The journey just begun.
Of course, we are not done yet. Obviously, we are working on agentic collaboration where agents are directly accessing data on user speed. We are also evolving our infrastructure to manage such agentic workflows. And finally, we are working on evaluation, benchmarking, and continuous improvement, the whole data flywheel, so that our system will continuously keep getting better. Thank you.